Good afternoon. I'm Philipp. I'm not coming from the academic world, as you might tell from my slides soon. I always describe myself, I'm from Vienna, city of fatty foods, classical architecture, and beautiful women. Thank you, Conchita. It's the only way to win for us. Yeah, I'm working for Elastic. Yeah, we're very much in the real world and actual projects. And today I want to talk about different databases, their use cases, and actually how we've come to this point. Like, where do databases come from and how have they developed over time? So when I'm not doing that, I'm running meetups in Vienna. And actually, this is an old slide deck you're using here. So this will be a lot of slides. Let's see how we get through that in 20 minutes. OK, so we're using databases. Everything started in 1970 with the kind of paper that started all the database stuff by COD, a relational model of data for large data banks. And the gist of that paper was basically like relational model and normal form, which led to data independence. Because the problem beforehand was kind of like you had different database implementations, but to use them, you actually needed to know very much in detail what they were using and how they were structured. And you would just implement your application just tailored for that specific application. But COD kind of said, like, this is a stupid idea. We'll just find a generic model, and we will build on that model so that it's pretty much the same for everybody, and we'll just have this generic model to use. So what he created was not the bottom line, that is SQL, which most of you are probably familiar with, but the middle line, the T is a free variable, etc., where he defines like the algebra. This is, I want to have all the people that are still living and which names are matching and in the amount of people. And this is what he defined. So he just defined the algebra, like the rules and what you define and how you define relationships. And then his colleagues at IBM found the actual SQL paper, giving what we know as SQL today. Back then, it was called SQL, and then there was a trademark dispute, and there was a product nobody knows anymore about that was also called SQL, and then they had to rename SQL, and they just removed a few letters and ended up at SQL. And kind of one of the funny anecdotes they told later on was that at some point, the guy called them and asked for all the specifications to use. And they assumed, like, well, at IBM, you could tell everybody anything, and nothing would happen anyway, so they just gave them all the information. And the guy who had called was Larry Ellison, and he used that information to found Oracle afterwards. And he is the only one who actually got really rich doing that. OK. The nice thing about that is, in general, that it is declarative. So you do not need to know how the database works internally. You just tell the database, I want to have this information, but you do not tell, like, I want to iterate over that data set, and you don't define, like, a for loop, a while loop, a do loop. You do not care. This is part of the query optimizer. You just define, I want to have this data, but you do not need to specify how to actually get it. And you can actually tell it is made for user interaction, so it was built for aggregations. You could easily put data together and aggregate over that. But there is other stuff users are not so good at, especially if they're not really trained computer scientists, like concurrency and integrity. So the database systems would take care of that for you. And then everybody kind of jumped on the bandwagon, and it was like buzzword-driven. Like, not only now we have buzzwords, but also back in the 70s and 80s we had buzzwords. And relational databases were kind of a buzzword back then. And then COD said, no, you're doing this all wrong. Like, here are 12 rules. Actually, there are 13, because like every good person in IT, he started numbering at 0 and went up to 12, so 13 rules. And he defined, this is what a system needs to do to be actually called a relational database system. And thanks to these 12 rules also, we have a very specific idea, like, what is a relational database system? And even though there are implementation differences, the general idea is very similar over all these systems. Yeah. And people started building databases, and they had no idea what they were doing. Which ended sometimes Yeah, sometimes they learned, sometimes they didn't, sometimes it ended very badly. But at some point, we kind of fell into a dark age of databases, and I always describe it like this. It looks something like this. You had these few very big vendors. They soaked up the entire market, like they bought the other competitors or kind of destroyed them. And then you were stuck with them. And there is Uncle Bob. He's very well known, at least in the Java ecosystem, and he has a very nice blog post about beer and databases, where he compares the state of databases to beer. Like in the 20s, when you were not allowed to sell any alcohol in the US, people forgot how to brew proper beer. And he said kind of the same thing happened with databases. That people forgot how to create proper databases, and then we were stuck with these big vendors, where in the US, where you were stuck with this horrible beer, and only in a few recent years, the microbreweries came up and stuff improved again. So the two motivations you have to, or why you actually want to get rid of the relational world probably is, the first one is, often relational databases are perceived slow and inflexible. It's like you have the turtle on the bottom, and your application would be the dog, and the dog would be much faster on its own. But the slow turtle on the bottom, which is your relational database, is holding you back. And then there was this paper, the CAP theorem, consistency, availability, and partition tolerance. This is actually what makes scaling up relational databases so hard, because you have these three attributes. You want to have all three of them, but you can only have two at most. If you design a bad system, you might only get 1 or 0, but at most you can get 2 of them. And the proof in the paper is actually very simple. It's kind of like you have a distributed system, assume you have 3 nodes, and the distributed system just breaks because the network in the middle breaks. And on one side you have 2 nodes, and on the other side you have 1 node. And then you want to write data to those 2 nodes. That will work probably. And then you want to read data on the other side. And then that one single node here, it knows something is fishy with the network. I cannot see the other 2. But what am I doing? Like, am I responding to that request? Then I will be available, but I won't be consistent. Or I'm not responding, then I'm consistent because I don't give out all the information. But the idea is you have a network split, which can always happen in a distributed system, and then your system probably needs to, or definitely needs to decide, like, do I want to give out stale old data, but I want to be available? Or do I want to be consistent? Then I'm not giving out any data at all. And in case you have children, you can describe this with Robinson Crusoe very nicely. Like, he's on his lone island, he's kind of partitioned from the rest of the world, and then a ship comes by and asks him a current question. Like, I think he was English, and people would ask him, like, who is the king of England now? And then he has 2 choices. Like, am I consistent? Then I'm not answering, because I'm not sure what the real state of the world is. Or am I available? Then I answer, but I probably give out an old or outdated information. And then there's the thing called eventual consistency, which you can think of like a message in a bottle. Every now and then he gets this message in a bottle, and then he's kind of up to date, like, 4 weeks ago, the King of England was King George or whoever. And that is kind of this eventual consistency, that after some point you will get an update, but it's probably not really the consistent state of what the world looks like right now. And then there are always people claiming, like, my network is so stable, this does not happen at all. Unfortunately, this is not true. There's this guy called Kyle Kingsbury. He has accumulated a large share of stuff that can go wrong in your data center from the biggest vendors like Microsoft, Amazon, Google. And on average, they will lose, I don't know, that many racks per day, and that many switches an hour, and that many data centers within a year. And it's just like, bad stuff will happen. And either you have been extremely lucky, or you're just not measuring it well enough to actually see what is going wrong in your data center. Yeah, and the second thing that kind of drives this thing where you need more than the relational world is schema flexibility. The first thing might be you just store bits and bytes on disk, and you have no structure. This is not helpful for anything that stores data. So the thing you need at least is something where you have a key and a value, and you can only access the value over the key. So you look a key up, and with that key, you get to the value. Then there is this like advanced data structures, whatever you want to call them, stuff like graphs. Like you have different nodes and edges between them, and you want to find the shortest path between these nodes. Or documents. Now JSON documents, because JSON is super popular in the IT world, so everybody needs to store JSON and query stuff with JSON. Or column-oriented families, which looks very much like a relational database with a table. But you often have these version values where you kind of add a third dimension, so you don't have only a row and a column, but you have a third dimension where you have different timestamps, different values. And you can also group them in so-called families together. Yeah, and then you have the rigorous schema. This was a good old relational database everybody has been using for 30 years or whatever. So these needs, like more schema flexibility, more performance, this is where NoSQL entered the market. And it is called not only SQL, but if you have ever been in touch with the recruiter, stuff like this might happen. Like the recruiter asks you, do you have a specific skill? And you say, no, I don't. And then they still need to put something in your resume to pitch you to a client. And then they just will put in your resume like, yeah, he's an expert in NoSQL. But actually, it's not NoSQL in not SQL, but not only SQL, because it's doing different stuff for other stuff. Yeah, and then this is also super popular. Big data always plays a role in that. Like, where does big data come in, and it will make you rich, and it will, yeah, help you to reach whatever goals you have. There are two definitions. One is very broad. It includes everything that is also in the NoSQL space, and the other one is rather for offline data and data warehouses, so like data processing. But I think it's mostly a buzzword, and I'm not too fond of having the word big data thrown around because mostly it doesn't mean much, it's just a marketing term. So now down to specific databases. Like there is a ranking of what is popular. Yeah, no, don't believe statistics you have not faked yourself. But we'll just use that, and we'll use some very popular open source implementations like PostgreSQL in the relational world, MongoDB, which is the most widely used NoSQL data store, Cassandra, Redis, and Elasticsearch for full-text search. So, MongoDB. What I'm saying about MongoDB is also true about everything that stores JSON, such as CouchDB, Couchbase, Elasticsearch, everything that is document-based. There's this very famous quote from Ted Neward, ORM, Object Relational Mapping, is the Vietnam of computer science, meaning stuff can go horribly wrong here, and I will show you why. I don't know how many of you are actually programming or programming in Java. This is one way to do an M-to-N relationship, which you can navigate from both sides. In case you have written something like this, do you think this is OK? Sign of hands. Has anybody written something like that? Yeah, a few, OK. But nobody thinks to seem this is OK, which would be like this, like, I'm OK, which is more like the Stockholm Syndrome, or you're still in denial. Why is there a problem? Let's assume we have some, that is all the code I'm showing, no worries. We have an abstract base class, and then we have managers who can approve funds, and workers who can actually do stuff. Managers obviously don't have any meaningful experience. And you want to store that in a relational database. So you have three options with relational databases. The first one would be you have a union table. Potentially it has many null values because you store everything together, and all the fields you do not have, they will just be empty. And you're missing out on stuff like not null constraints or other checks. So this is not really nice. What could you do instead? You could have concrete instances. Without common queries, you make one table for workers and one for managers, which works fine until the point where you want to get all the employees, like both managers and workers. Yeah, you can join it together, but again, it doesn't feel like it's really a good match. Or you can just have three tables, like you have one for the abstract base class employee, and then you have one for workers and one for managers. And every time you would want to access one, you would need to join it together. And in the object-oriented programming model, this actually fits together very nicely. Whereas in the relational world, it's just like there's this impedance mismatch. You cannot structure it as nicely or as equally as what you want to do. So in MongoDB or any other document store, you could do something like this, where you add a few annotations, and then since it's JSON and it's not as strictly enforced, you would just get the JSON documents with all the attributes you have, but there are no null values because it's just optional attributes. So you simply get something that is exactly the structure you have, which is very similar to what you have in your object-oriented programs. Which all works very nicely until you need to scale it up. In 20 minutes, we won't be able to cover that, but like scaling up might be a challenge there. Next up, Redis, which is called Redis for Remote Dictionary Server. And it's basically a key value store plus a bit more. We will look at one specific use case, like you have users, they can log in, and you want to know who has logged in during the last hour. The first use case you can use is each user who has ever signed up for your page gets a bit assigned. So the first user who has ever signed up for your page gets the first bit. The second user, the second bit. So for 1 hour, you just assign all the bits, set them to 0, and as soon as one of these users logs in, you flip the bit to 1 to set it that he has logged in. And for 1 million users, whatever time slice you want to use, it will be something like 120 kilobytes. So this is pretty small. The other data structure you could use has a very fancy name. It's called a hyperlog log, and it's a probabilistic data structure. So the nice thing is it uses just a fixed number of bytes, 12 kilobytes to be specific, to store unique elements, and you have an accuracy of 99% approximately. So you can be pretty sure if you want to query, like, has this user logged in, you can get the answer yes or no. And to compare the two, hyperlog log is super nice because it is constant size, whereas bitset is exact, and you can easily aggregate it. So if you, after a week, decide, I don't care like which user has logged in a specific hour, you can just aggregate or connect all the bits from that day, and as soon as he has logged in during one single hour of that day, you could just say, okay, that user has logged in during that day. Yeah, generally simple, and it's kind of an omnipresent glue. Yeah, next up, Cassandra, which is very good to scale up and down. And kind of its secret is the consistent hashing algorithm. And we'll quickly jump into that. So what you have is, you have a key space, you take a key, you hash that key, so it is evenly distributed. That is why you will want to hash it. And then it lands on a specific point in your key space, and it will go on that server. And what you then do is you rotate your key space clockwise, so it forms a circle. And then you know, OK, some data goes primarily on that specific node, and you will also copy the data to the next node, so you will know, OK, it is also replicated there. And yeah, that is how you can easily remove and add nodes. So the cluster will automatically detect that and change the key space depending on where you want to go and where it should be put. And you can actually store that in smaller slices, so it's more evenly distributed, but it should still work fine. Yeah, only thing is that one is not consistent, and it might be an issue for some people. So your father at some point might tell you this might be trouble. Or to put it more bluntly, it was so hard, we went with immediately inaccurate. Yeah, Postgres, the relational world. Often said, Postgres is super slow, but like this comic describes, it's mainly slow because you're using it wrong. And actually, relational databases are very powerful by now. SQL is a huge standard, and it can do lots of stuff. And it is so powerful that even the NoSQL databases are now providing SQL-like features, which is kind of an irony. You're a NoSQL system, and you're providing an SQL-like interface. And each one of them has their own special implementation, and they're all different, which just makes it more complicated. So Cassandra has the Cassandra query language. Google has its own thing. Couchbase was more creative. It's called Nickel, etc. So what you get in a relational world is generally like you have lots of maturity, just because these systems are way older than the NoSQL implementations. And you also get newer features because it's kind of they're taking over good ideas from the other side. Yeah, and then we have full-text search, which is interesting insofar like you don't just store content, you also remove stuff, like you remove any formatting, you parse data, you extract the single words you want to have, you remove stop words, which are very common but add very little meaning to your data, and you kind of stem them down to the word root, and then you store them. So this would look like we have 3 documents with some text. We remove the stop words, and then we have these words remaining. And we have a list like these words appear in these documents. And then you can say, in which document does the term blue and sky appear? And then you will see blue is in document 1 and 3, and sky is in document 2 and 3. So if you search for blue sky, only document 3 matches. And that is very efficient to do that once you have extracted all that information. And then you can actually score them like it's a quality attribute or how relevant something is, but we're not going into that. Like, if you have questions about that, find me afterwards and we can discuss that. And we have a full stack around that and released a major version yesterday about that. So, to conclude, this is not my slide, but it's commonly used. So because I always get tweets like, somebody else has posted that before you, yes. But it is super nice because 1970s, there was no SQL. In the 80s, it was no, you should know SQL actually. And in the 2000s, it was no, SQL is too slow and inflexible. Don't use that. And then 2005 is not only SQL, we can do more. And 2013 was no, SQL was actually probably not that bad. And for many use cases, it's still a good solution. So that is commonly, yeah, a reference. And then my final comic, like, it's my favorite one, is it fast? And this is like, under similar conditions, you're benchmarking 2 systems. And this is pretty much what everybody is doing when they're benchmarking their competitors. You're finding some similar condition which doesn't make any sense because the house cat has drowned. And the squid is not more intelligent, the other system is just dead, or you're using it wrongly. So yeah, that explains all the benchmarks. Don't believe any benchmarks. And depending on where you, or what you try to build, this is a few years old already, so some systems are not that popular anymore, but you can actually see where you will end up. And yeah, you can do that. I'm done. I think we're out of time. If you have any questions, find me afterwards. If you want to have some Elastic swag, I also have lots of stickers, and I'm happy to hand them out afterwards. Thanks.